Today's goal is to look at function composition and inverses. I think about function composition as being functions inside a function. Like if this were f of x and this were g of x, you can take a function and put it inside of another function, right? You're substituting every time you can, every time you see a variable. And in fact, you can take many functions and put them inside of other functions. Inverses are functions that undo each other, like multiplication and division, or addition and subtraction. Sometimes understanding functions and their inverses is really handy because it makes it easy to evaluate expressions, right? Evaluate means get the value, the number that it's worth, right? E to a power and natural log are inverse functions. They undo each other. So e to the natural log of 7 is just 7. 10, and this is the common log, there's no base written, so the understood base is 10. So 10 and the common log are inverse functions. They undo each other. So 10 to the power log of 3.2 is just 3.2. Now 10 and natural log are not inverse functions. Natural log has a base of e. So these do not undo each other. So 10 to the power natural log of 3.2 is just some number. You can type it into your calculator, or you can just leave it like this. There's no value that's really easy to find by hand. Okay, e to the natural log, they're inverses, they undo each other. You get 10 squared. E and common log are not inverse functions. You cannot undo them. Oh, here's an interesting one. 7 and the log base 7. So because 7 is to the power of log base 7, they will undo each other. You simply get k. Now, the log of 100 may not seem immediately easy how to simplify by hand, but if we remember that the log of 100 is the log of 10 squared, oh, well now you have a common log and 10 to a power. They will cancel each other out. They're inverse functions. You just get 2. Likewise, if you have the log of square root of 10, that's just log of 10 to the 1/2 power. Square root is the same thing as something to the 1/2 power. Log and 10 to a power are inverse functions. They cancel each other out. You get 1/2. Okay? Log base 2 of 2 to the 5th, you guessed it, is just 5. Log of, well, we can think this is the log of 1 over 1,000, 10,000, which is the log of 10 to the 4th, if 10 to the 4th is in the denominator. Well, that's just the log of 10 to the negative 4. Now we can cancel these out, you get negative 4. Okay, now on to number 2. Write the function d of x, oh d, it's a difference, of f of 2x minus 3g of x in standard form. Okay, let's do this in parts. If our function f of x looks like this, f of 2x means I just need to put 2x into the function f. That's like this. Every time I see my function f, if it has a variable, instead of putting x in, you're going to drop a 2x in there. So it'll look like 2 times 2x cubed minus 8 times 2x squared plus 5 times 2x minus 9. I'm just putting 2x into each of these x values. To evaluate, I use the order of operations, PEMDAS. I need to deal with the exponents first, so let's deal with this 2x cubed. That means 2 times 2x times 2x times 2x minus 8 times, you guessed it, 2x times 2x plus 5 times 2x minus 9. We have 2 times 8x cubed minus 8 times 4x squared plus, we can multiply this, 10x minus 9 gives us 16x cubed minus 32x squared plus 10x minus 9. Okay? If you were to have multiplied these 2's first and then cubed them, you would have gotten 4 cubed, which is 64. So be careful. Do not multiply these 2's. This 2 must be cubed first. 2 cubed is 8, then multiply by 2. Okay, this is f of 2x. We needed also 3g of x. So let's write our function. d of x equals f of 2x was this whole thing. 16x cubed minus 32x squared plus 10x minus 9. minus 3 times the function g. Doesn't look like we need to do anything to change g. So we'll just substitute 3x squared minus x minus 2. Okay, this 3 outside tells us we need to distribute. So we have 16x cubed minus 32x squared plus 10x minus 9 minus 9x squared minus 3x plus 6. We'll just combine like terms from here. Okay, and here's our function v of x in standard form, meaning it's not in factor form. You don't see parentheses of things being multiplied. Okay, now look at b. This notation looks like our function composition. We'll keep coming back to this. It looks like we're taking the function f of x and putting it inside of g of x. So let's evaluate. It's pronounced g of f of x. We'll take f of x, this guy right here, and put it in every time where we see an x value here. So we'll get 3 times 2x cubed minus 8x squared plus 5x minus 9 squared. We would have to square this term, minus 2x cubed minus 8x squared plus 5x minus 9 minus 2. Okay. This we could expand into standard form. We would have to multiply this term by itself, get out a gigantic box method, right, where we have 4 columns and 4 rows. That would be really nasty. We don't have to do that. It doesn't require us to write this in standard form. So we can say this is done. We did indeed put f of x, this function, into g of x every time where we saw an x. Take a look at c. C is also function composition. It's just using different notation. Okay? This notation is exactly the same as putting this function, the one that's written second, inside of the other function. In this case, both are h's. That's weird. We'll put h inside of it itself, but that's okay. Now, first we need to put 3x squared inside of h. So let's do that first. We have 6 times 3x squared minus 10. All right, well that just gives us 18x squared minus 10. Now we need to put h of 3x squared. So we're going to put this thing, that's h of 3x squared, into h again. So we have 6 times something. Last time that something was 3x squared. This time this something is a full expression. Again, multiply it out if you would like, or you're done. That's it. Okay, last one in this segment. F of h of negative 3. This time we're just putting a number into h. We'll put its result into f. So h of negative 3 is 6 times negative 3 minus 10. You guys have been doing this for a long time. You get negative 28. So f of h of negative 3 is just f of the result, negative 28. And again, you're just going to get some number once you put negative 28 into each of these places. All right, let's move on. Determine if each function is invertible. Invertible means its inverse is a function. That means for its inverse, every input has one unique output, okay, over its domain. Explain, if it's not invertible, restrict the domain. If we look at the sine function, take a look at these points. It's a little hard to read. It says this is 0.5 pi. You have this point 0.5 pi, comma 1, and this point, which is 2.5 pi, comma 1. If you take its inverse, an inverse function undoes. It's going to switch inputs and outputs. So the inverse function will have the points 1, 2.5 pi, and 1, 0.5 pi. Now the input 1 has 2 different outputs, so the inverse is no longer a function. So we have to restrict its domain. Let's just start labeling some points and see where we need to leave off, okay? If we've got this point 0, 0, and we invert it, the inverse has the function 0, 0, Okay, no problem there. We've already got this point, 0.5 pi 1. That means we can't include this point, or else the input 1 has more than one output. Oops, excluded the wrong one. We'll take this guy out. If we include, so we can include these guys. If we go over to here and we include the point pi 0, then we'd have the point 0 pi, and that's no good because now the input 0 produces two different outputs, 0 and pi, so can't have this guy. All right. So it doesn't appear we can go further in this direction. Let's try going further in this direction. If we include negative 0.5 pi, negative 1, our inverse function will have the point, I'm just switching the x and y values, negative 1, negative 0.5 pi, totally fine. So let's include these guys. If I go back over here and have negative pi 0, then I've got the point 0 pi. Again, my input 0 will be producing two different outputs, so that we can't have. It looks like my function will be invertible. That is, the inverse will be a function if, for example, I restrict the domain to negative 0.5 pi up to 0.5 pi. I can include these points as well. Okay, let's move forward to one last problem. Let's prove whether or not these two functions are inverses. There are two different ways you can prove. One way would be to calculate the inverse function and see if the function you got was the other function that's listed. There are two functions listed. The other way to prove, traditionally, when you get into higher level math classes, the functions get more and more and more complex. So sometimes it's hard to prove directly, and so you want to use function composition. Sorry, this is hard to read. If you use function composition, if they're inverses, they'll undo each other. So you start with some x value, and you do a function, let's call it f. You get some y value. The inverse function is going to switch x and y, so it'll start with y. It should give you that same x value back. So if these really are inverse functions, and we use function composition, f of g of x will be x, and g of f of x will be x. Let's start. Here are my functions. Sorry, they're hard to read. F of x, there we go, is negative 1/5 e to the x plus 7, and g of x is natural log of 5x minus 7. So if we take f of x and put it inside of g, we'll get the natural log of 5 times, now we need to put this whole function f in, negative 1/5 e to the x plus 7 minus 7. Right? Natural log of 5 times something, here's my something, minus 7, and yep, the something is that function f. Now, it's nice to think like, let's just start canceling stuff out, but we have to be really careful about canceling them out in an order that makes sense. Here you're multiplying 5 by a bunch of stuff. All of this stuff, this e to the x plus 7, is also being multiplied by negative 1/5. Well, multiplying by 5 and negative 1/5 makes this negative 1 e to the x plus 7 minus 7. I would really like to cancel out those 7s, but I gotta distribute the negative 1. So this would be the natural log of negative e to the x minus 7 again. This is already enough evidence to show this is not x. And because they didn't simply reduce to x, you can conclude already g and f aren't inverses. If they were inverses, g of f of x should have reduced to x, and f of g of x would have also had to reduce to x. In this case, we're already done.